everyone, and welcome to the video on the fundamental theorem of algebra. So in this video, we're going to discuss the fundamental theorem of algebra. We're going to look at the definition of it, but mostly what we're going to be doing is we're going to be looking at the consequences of it. So okay, we know what fundamental theorem of algebra is, but what does that mean for us, and what can we do with it, and what kind of opportunities or different ways of solving problems does this allow us to do, or what kind of information does it give us? So that's what we're going to be looking at in this video. So what is it? So what is the fundamental theorem of algebra? So a technical definition is it means every non-constant polynomial, so just think of polynomial with a variable. So this is just, does your polynomial have a variable in it? Great, it's a non-constant polynomial. With real or complex coefficient has at least one complex zero. So remember, the reals are also a subset of a complex, of the complex. So the number 15 is still a complex number because it's really 15 plus 0i. It qualifies as being complex. So this is basically saying that every non-constant polynomial has at least one zero. We'll just say zero now in general. A consequence of that, or another interpretation, is a polynomial has as many real or complex zero as the degree of the polynomial. So which means x to the fifth plus 3x squared plus 5 has 5 zeros, because remember, highest exponents, that's the degree. So the degree of the polynomial is also the amount of zeros that it's going to have. So this is the main way we're going to use fundamental theorem of algebra. Or if we see something like x to the third plus 7, that means this polynomial is going to have 3 zeros. They may be real, they may be complex, we're not sure. Remember, complex solutions appear in conjugate pairs. And that's something we'll see a little later in the video. But again, if we see something like x to the 7th, I don't know, negative 5x to the 7th plus 3x squared minus 5, this polynomial is going to have how many zeros? Hopefully you got it. 7. Yes. There's going to be 7 zeros of this polynomial. So the degree of the polynomial will tell us how many solutions we have. They just may be real or complex. So what are the options for the natures of the roots? Well, what we just said, well, they may be real, right? We may actually see them on the number line. We may actually see the polynomial cross the x-axis, in which case we'll have real roots or real solutions for the polynomial. Or they could be complex, but complex always occur in conjugate pairs. So if one of your solutions is 3 plus I, the other solution has to be 3 minus I, okay? And these both have to occur. So if you find one complex solution, then the conjugate pair is the other complex solution, okay? These guys come in pairs, which means odd degree polynomials will always contain at least one real root. At least one real root. Sorry for the sloppiness there. Why? Because, well, if conjugate solutions occur in pairs, well, I can't pare down 5 because it's odd, which means it has to contain one real root, which we also know because the shapes of odd polynomials go like opposite disco fingers, and at some point they got to cross the x-axis, so there's always at least one real root for odd polynomials, unless you restrict the domain. So what's an easy way to know the nature of the roots? Be like, okay, well, I have a polynomial that looks like x to the 4th plus 3x cubed minus 3 or something. How do I know how many real roots there will be? So I know there's 4 roots. But how do I know how many of these roots are real and how many are complex? Well, Descartes' rule would tell you that. We're not going to go over that in the scope of this video, but there is another video on Descartes' rule that you can go visit. But Descartes' rule would tell you that. Graphing it would also tell you some information, but it's limited because not all graphs are going to show you every piece of information that you need. And you also need to be familiar that if you have, these bounce back points, that's a real zero, but it's multiplicity of 2, so that zero actually counts for like 2 zeros. Or if you have an inflection point at the zero, so it's like going concave up and then it's going concave down at that particular point, that's a multiplicity 3. So when you see a bounce back point, that's a multiplicity 2. So the graphing thing is limited. The best way is Descartes' rule, so go check out the video on Descartes' rule for that. But we are going to do it all today with graphing. So this is going to be a simplification of fundamental theorem of algebra. So what is the nature of the roots? So this is, we're going to focus on graphing here. So what's the nature of the roots here? Okay, well, how many roots do I have? Well, I have 3 roots. And according to my graph, so here's the x-axis, here's one x-intercept, and it's a straight pass-through point, so it's multiplicity 1. So that's one real root, so one real root. So if I have one real root, how many complex roots do I have to have? Well, then there's going to be 2 complex, and there'll be a conjugate pair. So from a graph, I can see this way. All right, what about this example? And I've highlighted a couple of the intercepts here because they were a little hard to see. Well, how many, let me move my pen tool down a little bit. How many roots should this polynomial have? Yeah, 5, right? Because that is the degree of the polynomial. So this thing should have 5 roots. And this is all consequences of fundamental theorem of algebra. So this thing should have 5 roots. How many real roots do we see? Well, here's one here. And then here's 2 here. This is why I highlighted them, because they were hard to see. So there's 3 real roots, and all 3 of these roots are straight pass-through points, so they all have multiplicity 1. So this guy's going to have 3 real roots, and then how many would have to be complex? Well, the 2 remaining would have to be complex, okay? So this is how graphing can show us some information. Like I said, this won't work always, because when you get into very, very high degrees, visually, intercepts start getting a little confusing to look at, and to see the multiplicity isn't always completely clear because you're doing a visual inspection. The more precise way to do this, again, would be Descartes' rule. All right, so go, again, check out the Descartes' rule video if you really want to see how to know the nature of these roots. All right, so here's another example. So according to fundamental theorem of algebra, so what is the lowest possible degree of this polynomial? Well, I know from visual inspection, as many times as this polynomial could pass through the x-intercept, or sorry, the x-axis, could tell me the degree. So this is what I mean. So here's a bounce back point here, and here's a bounce back point here. So I know, and let me know this with a different color. So here's a bounce back point here, here's a bounce back point here. So I know that's a multiplicity of 2, and I also know this spot is a multiplicity of 2 as well. And then we pass through here. That's a straight pass-through point, so that's a multiplicity of 1. All right, so the lowest degree of this polynomial could be 2, 3, 5. And we know it's an odd degree polynomial because it has disco fingers, right? It's going opposite direction. So the lowest degree of this polynomial then would be 5. We can also look at how many turns this thing has, right? How many times it changes from going increasing to decreasing. The changes, how many changes we have, that'll also tell us. So if I clear this, so we're increasing, and then we're decreasing. And then we changed, so now we're increasing, and now we're decreasing, and now we're increasing. So that's 1, 2, 3, 4, 5, I'm going to call these like directional changes. So this will also tell you that this was at minimal a degree 5 polynomial as well. So there's a couple of different ways you can think about this. So you can look at how many turns, quote unquote, it has, in which case it has 5 turns. Or you can check out the intercepts and you can look at the multiplicity of all the intercepts and you can add those together and that would have gotten you 5 as well. So we've talked about so far just the nature of the roots, but more specifically now I'm like, okay, great. Well, I know I have 2 real, I know I have 2 complex, but what are they, right? So there's some strategies that we can use, and the strategies that we're going to use in this video, we're going to use a combination of graphing, factoring, synthetic division, and quadratic formula. Outside of this video, I would also suggest, my pen tool, I would also suggest rational root theorem, and Descartes rules, Descartes rule. That's how I remember how to spell it. So these two we're not going to use in this video, but go watch these guys too. That'll give you a little more information. So the full list of strategies that we could employ would include rational root theorem as well as Descartes rule. But this video, again, is designed to be kind of more simple. So we're not going to go over these guys. We're also not getting into super high powers of polynomials either. But just to know, the full list here would be these guys too. So let's do 2 examples. So find all the solutions to 3x cubed plus 16x squared plus 55x plus 52 equals 0. Now I have the graph here already. So I use the strategy of graphing. First off, trying to do these problems, there's no like, here's the one way to do it and you have to do it this way every single time and this is the only like algorithm cookbook recipe to do it. Finding zeros of polynomials, especially when you get into really, really high degrees, is more like detective work. It's like, okay, well, I found 1 0, and that'll lead me to the next 0. It's like getting one clue, and one clue will open up the door to another clue, and that clue will open up the door to another clue, and you just kind of keep going down the rabbit hole until you have all the clues. Except for in this case, I'm going down and finding all the zeros, and 1 0 is leading me to the next 0, which is leading me to the next 0. Okay, but again, it's a lot of detective work. It's figuring out. So all the solutions to this, so the strategy that I use, which again is not the strategy you always have to use, I graphed it and I got an intercept at negative 1.33333 forever. I know as a fraction this is equivalent to negative 4/3. So I know right now my first 0, and actually my only real 0, occurs at negative 4/3. So I have one real 0 at negative 4/3, which is going to imply what I'm looking for now is 2 complex zeros. And the complex zeros I'm looking for will be complex conjugates of each other. Okay, so this is the first step in our detective work. I know I'm going to have 1 real 0 and 2 complex zeros. I know my real 0 occurs there. Okay, so if I have a real 0, how can I continue on to find the other 2? Well, this is where synthetic division comes in handy. So put the real 0 that I know here in the window, and coefficients 3, 16, 55, 52, first number drops down, negative 4/3 times 3 is negative 4, add these together, you get 12, multiply negative 4/3 times 12 will be negative 16, add these together, I'll get 9 and 3, or 39, negative 4/3 times 39 gives me negative 52 to 0. Okay, good. So that was a factor. So now let me rewrite the polynomial. So drop the original power by 1. So this will be 3x squared plus 12x plus 39. Okay. So now, I have 1, 0. So now I've reduced my polynomial to a quadratic. Let me try to find the other two. Well, I already know that the other two are going to be complex. So I'm going to throw out factoring right away, and I'm just going to try to launch into quadratic formula, because quadratic formula will tell me what the other two complex zeros are. So now I'm going to do quad formula. Okay? So remember, there's our A piece, there's our B piece, there's our C piece. So quadratic formula, negative b plus or minus the square root of b squared, which is 144, minus 4 times a times c, and I'm going to have to get a calculator out because these numbers are getting a little big, and mental math for big numbers is honestly not my strong suit, and 2 times a on the bottom. Okay, so let's simplify this. So negative 12 plus or minus the square root of 144 minus 4 times 3 is 12. 12 times 39 is 468. So 144 minus 468 is going to be negative 324. No, I did not do that in my head. I totally had the use of a calculator. There's no shame in my game with that. All right. Reduce this radical here. I happen to know that the square root of 324 is 18. So we'll have negative 12 plus or minus, so then the square root of negative 324 will be 18i all over 6. Now we can divide by 6, divide by 6, divide by 6. So what do we get here as our other two complex solutions? Over 1, so we'll get 2 plus or minus 3i, which means our other two solutions. So we know our first solution was negative 4/3. We got that from the graph. To minus 3i, and its conjugate to plus 3i. Boom. There we go. Employing all of our strategies. Employing synthetic division. Employing quadratic formula. Employing graphing. Employing how we know the nature of our zeros. So it all kind of came together in this particular problem. So let's do another one, and this will be the last one. So the last one is, so we're going to raise our power a little bit, and we're going to change the nature of the problem. So we're not just trying to find the zeros. Now what I want is I want a full factorization of this guy. So every polynomial does have a full, what we call a linear factorization, which means this guy is going to break up into a bunch of factors, right? Dot, 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 dot. And they could have some multiplicities on them. They won't be that high because our leading exponent is a 4, but that's what we're going to do. We're just going to break it up into all of its factors. But to break it up into its factors, we need to know its zeros. So we know there's 1 0 at x equals 2, so that's a big hint for us. So if we know that there's 1 0 at 2, we'll throw that into synthetic division right away. So 2 goes up in our window. Our coefficients are 1, 2, negative 2, 12, and negative 48. So first number drops down. 1, 2 times 1 is 2. Add 4, multiply 8, add 6. Multiply 12, add 24, multiply 48. Hey, we zeroed out. Good, because we knew that was a 0. Our new polynomial dropped the power by 1, so this would be x to the third plus 4x squared plus 6x plus 24. All right, and equals 0 because I want to now try to find the zeros of this polynomial. The strategy I'm going to employ now, because I can see it, I'm going to factor it, and I'm going to factor by grouping. This, again, the strategies that I'm using aren't going to work always. Like I said at the beginning, this is more like detective work, and you've got to kind of see where 1 0 leads you. So this particular 0 leads us into being able to do factor by grouping. So common factor here is x squared. Then we get x plus 4 left over. Common factor here is 6. and then we'll get x plus 4 left over. Perfect. So this will break up into x squared plus 6 times x plus 4. So what do we have so far? So if there was a 0 at 2, then the factor is x minus 2. And we just found out that the rest of the factors are going to be x plus 4 and x squared plus 6. So now what we need to focus on is we need to focus on this factor here of x squared plus 6 because it's not a linear factor. So we need to break it into linear factors. In other words, we can't have this square here. So now I'm going to pull that out and I'm going to work on this. So how can I make x squared plus 6 into the product of two linear factors using either real numbers or complex numbers, right? Well, we could throw it into quadratic formula, or we could use our knowledge about complex conjugates. So remember, sum of squares does not exist in the reals, but it does exist in the complex. Now, every number can be considered a square because we could just use its square root, right? So for instance, if this was a subtraction, we could use x plus root 6 and x minus root 6, and that would get us x squared minus 6, but we have x squared plus 6. So the handy thing here, just append the I out front, and that's it. Okay, so if you're trying to factor a sum of squares which has no factorizations in the reals, treat it as a difference of squares and just append the I because it does have a factorization. It's just going to be in the complex. So now let's write all of our factors. So the factorization we're going to have is going to be x minus 2 from the 0 they gave us, x plus 4, which we got from our factor by grouping, and then let's break up x squared plus 6. It's going to break up into x plus I root 6 and x minus I root 6, or you could write the I after the root. I just don't do it because with my writing it looks like it's in the root and it's not supposed to be in there. Alright, so here would be our linear factors. And look, there's 4 of them, and it was a degree 4 polynomial. Fundamental theorem of algebra. So I hope you guys enjoyed this video. I hope it helped. I hope you guys learned something. And then as always, if you guys have questions, please don't hesitate to ask.